We now discuss the solution of a problem from the section linear algebra. The problem is on the nilpotent matrices of index 2. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the part C. The given question is, let m belongs to mn over the set of real numbers such that m not equal to 0 but m square is equal to 0. Then which of the following statements are true? We are given four options. Option 1, if n is even, then the dimension of the column space of m greater than the dimension of null space of m. Option 2, if n is even, then the dimension of column space of m less than or equal to the dimension of null space of m. Option 3, if n is odd, then the dimension of column space of m is less than the dimension of the null space of m. Option 4, if n is odd, then the dimension of the column space of m greater than the dimension of the null space of m. We are given a matrix capital M, which is an n by n matrix with real entries such that m is not a zero matrix but its square, that is m square, is equal to 0. Then we have to discuss which of the following statements are true. The four options are given to us. That is our given question. We now discuss the solution of the problem in detail. We have M, an n by n matrix with real entries, which is not a zero matrix, but its square, m square, is the zero matrix. This implies M is a nilpotent matrix of order n of index 2. M is a nilpotent matrix of order n of index 2. Now, in the options, options are given in terms of dimension of column space of M and the dimension of null space of M. Let's see what is dimension of column space of M. That is equal to the column rank of M. And we know the column rank of any matrix is equal to the row rank of the matrix is equal to the rank of the matrix. Therefore, column rank of M is equal to row of M. That is the rank of M. Dimension of the null space of M. And the dimension of null space of M is called the nullity of the matrix M, and it is denoted by n of M. Now, because we are getting the rank and nullity here, we recall the rank nullity theorem. So, for any square matrix of order n with real entries, the rank of M plus the nullity of M is equal to number of the columns of the matrix, that is n. We continue in the next slide. We recall the following result. If A and B are matrices of orders m and n and of orders m cross n and n cross p, then rank of A plus rank of B minus n is less than or equal to the rank of the product AB is less than or equal to the minimum of rank of A, rank of B. A and B are matrices of orders m by n and n by p. Therefore, they are compatible for multiplication. Thus, we can define AB. Then, the result says rank of A plus rank of B minus n, the number of the number of columns of A, which is equal to the number of rows of B, that is minus n, less than or equal to rank of the product AB is less than or equal to minimum of rank of A, comma rank of B. Let's call this as the equation 1. If M is a nilpotent matrix of order n of index 2, then we will prove rank of the matrix M is less than or equal to n by 2. So, in the above result, put A is equal to B is equal to M. So, if we put here rank of M plus rank of M minus n is less than or equal to rank of M into M, that is rank of M square. But we know M is a nilpotent matrix of index 2, M square is equal to 0. And row of M plus row of M is 2 times row of M minus n less than or equal to rank of the 0 matrix, that is 0. So, this will imply 2 times rank of M is less than or equal to M, this n. This implies rank of M is less than or equal to n by 2, hence the result. So, if M is a nilpotent matrix of order n of index 2, then the rank of that matrix is less than or equal to n by 2. It is a general result, and we require this result here. And we have already proved if M is a nilpotent matrix of order n of index 2, then rank of M less than or equal to n by 2. Let's take the first case. Case 1. Let n be even, say 2k, that is n is equal to 2k. Then rank of M less than or equal to n by 2 means 2k by 2, that is k. So, rank of M less than or equal to k. Now, we use the rank nullity theorem. Then the nullity of M is equal to the number of columns, that is n is 2k minus rank of M. But rank of M is less than or equal to k. So, this will be greater than or equal to 2k minus k, that is equal to k. This means the nullity of M is greater than or equal to k. Then rank of M less than or equal to k, but k is less than or equal to nullity of M from the above. So, combining these two, rank of M is less than or equal to the nullity of M. Now, what is the rank of M? The dimension of the column space of M, which is the column rank of M, which is equal to rank of M. This is the dimension of column space of M less than or equal to n nullity of M, that is the dimension of the null space of M. So, let us recall our options. And the result what we have just proved, the dimension of the column space of M less than or equal to dimension of the null space of M, which appears against option 2. Therefore, the option 2 is true. And in the light of this result, the above option 1 is not true. So, thus we have proved option 2 is true and option 1 is not true. We continue. That's what we have. Rank of M less than or equal to n by 2. Let us consider the case 2. Let n be odd, say 2k minus 1, that is n is equal to 2k minus 1. Then rank of M is less than or equal to n by 2, n is 2k minus 1 by 2, that is equal to k minus 1 by 2, right, which is less than or equal to k minus 1. This means to say that the rank of M is less than or equal to 2k minus 1 by 2, which is the greatest integer not exceeding 2k minus 1 by 2 is k minus 1. It amounts to that, to say that. So, anyway, the rank of M is less than or equal to k minus 1. Now, we apply the rank nullity theorem. nullity of M is equal to number of columns, that is n. N is equal to 2k minus 1 minus rank of M. And rank of M is less than or equal to k minus 1. You apply here. It is greater than or equal to 2k minus 1 minus of, in brackets, k minus 1. And that is k. That is k. Now, thus we have proved the nullity of M is greater than or equal to k. Agreed. Now, the rank of M is less than or equal to k minus 1. Yes, here less than or equal to k minus 1. But k minus 1 is strictly less than k. And k is less than or equal to the nullity of M. Agreed. Combining these two, we get the rank of M is strictly less than nullity of M. That's what we have proved. And let's look at our options. And the rank of M means the dimension of the column space of M, less than nullity of M means the dimension of null space of M. Let's look at our options. And what we have proved is dimension of the column space of M is less than dimension of the null space of M, appears strictly less than, appears against option 3, right? So, and so the option 3 is true, and the option 4 is obviously not true because it is less than, but in option 4 it is given strictly greater than. It is not true. It is not true. So thus we have proved option 3 is true, option 4 is not true. So combining these two cases, we get the answer option 2 and option 3 are true. So that is the answer of this question. And that is the detailed discussion of the solution of the problem, which is based on the properties of nilpotent matrices of index 2 from linear algebra. And I am sure that you have understood the solution of this problem. And I wish you all the best. Thank you.